The respiratory quotient is this weird part of the course, the respiration topic, that doesn't really fit in as well as the others, because the others tell quite a nice story and you get a decent understanding, but respiratory quotient doesn't, so it's hard because you don't really feel like you get it. But if you remember this equation, you're not going to go too far wrong. So it's CO2 released over O2 uptake per unit time. And the respiratory quotient will pretty much always be between 0.7 and 1. The only time that it will go sort of outside this range is it sometimes will go above 1. If this happening, I'm not going to explain why, because it takes ages and you won't fully understand it anyway. It is anaerobic. So if you have it going above 1, anaerobic respiration is going. So that's the sort of first part. Then, for when you're respiring glucose, that's fantastic. You just look and you go, fine, wicked, perfect. Okay, so we've got 6 O2 going into 6 CO2. So we've got 6 CO2. So if we go to chemistry, you can go, we've got 6 moles of CO2. If you don't want to go for moles, just doing grams. Okay, it's the exact same thing. For 6 grams of oxygen going in, you get 6 grams of CO2 back. Okay, so then you go, okay, well, then I've got 6 moles of O2 going in. So that just means I've got a respiratory quotient of 1. So when you see something, and if you do a calculation, and they give you some calculations to do and the respiratory quotient is 1, that means you are solely digesting glucose. However, we know that's not the case at A-level. That isn't true at A-level anymore. The idea that you'd solely respire glucose doesn't give a full story. Your body will be using lots of different things that it can. May that be glycerol from fat metabolism, or even using a few amino acids. Or, coming in as our acetyl group, we've got our fatty acid. So fatty acid chains can be then taken into acetyl. Basically, because these pathways, so these arrows are massive simplifications. Massive simplifications. There's loads of different sort of reactions that go on that make it into acetyl-CoA. It offsets this beautiful one-to-one balance that glucose has. And what ends up happening is that if you're actually respiring proteins, you'll get a respiratory quotient of 0.9. So for every oxygen that is used, so say we have 1 gram of oxygen used, you'll have 0.9 grams of CO2 released. And that's all it means. It just means that if you were to measure it, that is what you would get. It's very rare that they will actually ask you to measure it. I'm going to show you an example later though. And with triglycerides, it's even lower. So for every single mole of oxygen, so if you get 1 mole of oxygen in, or 1 gram of oxygen used, actually you're only going to get 0.7 grams of carbohydrate back. Carbohydrate, CO2 back. Okay, that's all it's saying. So, if they give you something like this, you just go, fine. Find the RQ value for tripalmitin. I don't know what tripalmitin is. I don't think anyone does. Maybe they made it up. Who knows? But what you do is you go, okay, so for every, so 100, alright, so 145 moles of O2 are being put in, so that's our uptake, and 102 CO2 are coming out, which will give us an answer like 0.703, which is roughly what we wanted. We said triglycerides give us about 0.7, so that fits what we know. Explain why the RQ value for respiration in human is usually between 0 and 0.7 and 0.1 is because it's usually aerobic. Okay, because if it goes over 1, then it's anaerobic. And also we've got mixed substrates. So it's very rare that you're just doing glucose. It's a mixture of all of these. So it'll usually sit somewhere between, because the triglycerides will bring the average down, the glucose will bring it back up, and the protein sits somewhere in the middle.